Okay, guys. So what happens under fasting conditions, right? When glycogen stores have been completely depleted and all you have available is other sources of carbon equivalents. You don't have any more glucose, right? Like I said, we've got these glucose dependent tissues. We got to make glucose, right? And under those conditions, under fasting conditions, when your glycogen stores are basically run down, right? Your only option is to make glucose and basically make it from non-carbohydrate sources. So under these conditions, cells will use this gluconeogenic pathway, this fundamentally anabolic pathway, to make glucose from and this is key, non-carbohydrate sources, which is going to involve 3-carbon and 4-carbon sources, right? Okay. Now, this process of creating glucose from these non-carbohydrate 3-carbon and 4-carbon backbones, like I said, is under starvation conditions, it's the only shot you've got, right? You've got to come up with a way to make the glucose to keep those key tissues running. But even under non-starvation conditions, this pathway is an important thing, right? Your body, as you guys may know, is constantly worrying about this balance between stored glucose and glycogen, glucose utilization, and all these tissues around the body, right? So maintaining a balance between blood plasma glucose levels, the demands of peripheral tissue, stored glucose as glycogen is a really big deal. And organisms like us work really, really hard to maintain that glucose level, a circulating blood glucose, in a pretty narrow range. And when that gets screwed up, right, of course, we recognize when that creates a disease state like diabetes, right? But there are also a whole set of glycogen storage disorders when that glycogen mobilization and storage process gets messed up, right? So all of this is tied up together in this really important set of catabolic and anabolic pathways and how they're connected and regulated to maintain blood glucose levels in a very narrow range in organisms like us, right? Okay, so how does that work, right? Seems like that's a pretty big deal, right? Okay, well, you might guess, right? You may know gluconeogenesis basically is going to be, in a big picture sense, the reversal of glycolysis, right? So back to this sort of like 35,000 foot view map of central metabolism, glycolysis was coming down this way from glucose down to pyruvate. Essentially what we're going to do is we're going to turn around and go the other way, right? So a little bit more narrow view here again, process of glucose, here we are going back up. Now this map sort of suggests that we could take the acetyl-CoA equivalents and go back up to pyruvate. Organisms like us can't do this, right? So that little blue arrow right there, that's wrong. We can ignore that. We don't have the enzymes to do that. Mammals, most other multicellular organisms, like or higher eukaryotic organisms like us, can't run that reaction. We don't possess the enzymes capable of reversing the pyruvate dehydrogenase reaction. Many plants can, but mammals can't do that, right? Which is why we can't turn fatty acids into glucose, right? But for the case where we have pyruvate, right, or we have some other 3-carbon source of stuff, right, like backbone equivalents from amino acids, there is a way to do this, to turn these equivalents back into glucose by going essentially back up this pathway. Okay, but here's something to think about. Where you guys remember where the glycolysis enzymes of the glycolysis live, right? They're in the cytoplasm. Guess where the enzymes that are going to do this gluconeogenic pathway, where do they live? They're also in the cytoplasm, in the same place. So here's a question: why does this even work? Why isn't glucose, where we've taken, say we're gonna worked hard and we've made pyruvate, for example, and we run this back up to make glucose, why doesn't it just get burned right back off again by glycolysis? Why don't you then have, in principle, a futile cycle, right? Seems like that'd be a disaster, because as you're going to see, running gluconeogenesis is not cheap, right? This costs energy, right? And the whole cycle, if you think about the consequences of the second law of thermodynamics, is going to expend even more energy. It's going to be an irretrievable loss. There's no way to make these perfectly balanced, right? So it's going to cost energy. It's worth doing because it's good to keep your brain running and your blood circulating and supplying oxygen. So it's worth it in a big way, but it's going to cost energy. So why doesn't it just burn right back off, right? Okay, well, the answer to that is somewhat general, right? And it's general in the sense that it's frequently true, if you look at this 35,000 foot view map, that these catabolic pathways are paired with reverting anabolic pathways. In most cases, not every case, but in the utilization of amino acids or their catabolism or their anabolic production, right? Same with making glycerol, fatty acids, nucleic acids, right? They're almost always paired anabolic catabolic pathways. This is sort of the yin yang of basic biochemistry. So that issue of facing futile cycles exists all over the place. Now, one solution is to potentially spatially segregate these, but in many cases, that's not true. These things are happening in exactly the same compartment of the cell. So how do you avoid futile cycles that would be wasteful and deadly in the long run? The answer to that question comes down to a couple of things. How the pathway in one direction or the other is constructed, right? And they're not constructed the same way. That's point one. The second point is how they're differentially regulated, right? And it's really important that what's going to be turned to be true is the catabolic and the anabolic pathways are very, very carefully coordinated so that only one is running under a given physiologic state. So it's like a toggle. You want to run anabolically, you turn the catabolism off. You want to run catabolically, you turn the anabolic pathway off, right? So those two things, pathway design and regulation, are going to be key to understanding how futile cycles are avoided, right? Okay, so let's think about this again from sort of a bigger picture. How would you do that, all right? If you're not going to spatially segregate things in like completely different compartments of the cell or different parts of an organism, how do you use pathway design to avoid it, right? Okay, well, like I said, the first general principle, design principle here, is that the anabolic pathways that are paired with a given catabolic pathway are never the exact reversal in terms of this exact steps. It never works that way. You don't just take glycolysis and then make an exact reaction for reaction direct reversal, right? The reason for that is glycolysis is actually really pretty exothermic, right? The overall free energy balance for glycolysis is somewhere in the range of about minus 100 kilojoules per mole, right? The direct reversal of that process would be massively expensive. You'd have to expend significantly more energy than that to try and crawl back up exactly that same set of steps. And that big energetic difference also would make that reversal almost impossible to regulate, right? You'd have almost no way to apply sufficient regulatory power to differentiate those two pathways, right? Okay, so the solution here is to not try and do it that way, right? And there are two general ways in which one could build a pathway that gives you both the control and solves that thermodynamic problem. All right, the first is to build a pathway, a reversing pathway that uses a completely different set of steps, right? So you can imagine if we had, say, this was glycolysis and we came down here all the way down here to pyruvate, right? Well, I want to build a pathway that goes the other way. I could come up with some different intermediates, take some different steps, follow a different route that's not as hugely expensive as going right back up this way. And then I need a set of, enzymes that run the anabolic pathway up this way. So they're totally separate, completely different intermediate, completely different enzymes, right? Okay, there's another way to do this. It's simpler, right? Let me see if you recognize maybe where this is coming from. An alternative way to do this is to actually build your pathway so that many of those steps operate near equilibrium. In other words, the free energy change is either close to zero, standard state, or maybe is even positive in one direction, right, or the other, right? So they operate with maybe an intrinsic bias, but they're operating essentially somewhere close to equilibrium. And then what you do is you have a key step that sets the flux in either the forward or the reverse direction, right? So here we have a bunch of steps. In principle, I could pull these either way because they're operating by virtue of both the standard state free energy and or my ability to manipulate the concentrations of these pools close enough to equilibrium that I could push them either way, right? Same here on the either side. But then at some key step, some critical, usually energetically expensive step, I differentiate the pathways. I have one pathway that if I want to run catabolically, I use my enzyme 3, right? And if I want to run the pathway anabolically, I say, I use this enzyme 6, right? Notice something. To get this pathway to run, I only need one additional enzyme. All the rest of the enzymes in the forward pathway are exactly the same, right? In fact, 4 of them, this pathway design, are identical in both pathways. And at that point, if I make this enzyme, E6, right, my focal point, the differential regulation I have to now impose is a lot simpler, right? Because in this case, right, for the forward pathway and the reverse pathway, ideally, I'm going to have to reciprocally regulate E1 in this separate pathway, or E6, right? I have to turn one on, turn the other off. But these other enzymes can't interfere, right? Somehow, either by design of their intermediates or by controlling their expression level or something, these guys kind of have to stay out of the way, right? This pathway design, they're the same, right? All that matters is that I control by differentially regulating, same way. So either this guy or this guy, depending whether I want to run up or down, either turn this enzyme on or I turn this enzyme on and turn the other one off, right? That lets me use the intrinsic energetic balance between these other steps as a way to push the pathway whichever direction I want by depleting intermediates on one side and pushing by producing intermediates on the other side, these steps that are close to equilibrium, right? And all my regulation happens, and my key sort of bypass steps happen at 1 or 2 points that let me get around those key energetic nodes, right? And parsimoniously preserve the number of enzymes I need. Now, if you think back to all the discussions we had, and we were thinking about glycolysis, all those steps that seem to be operating, with a bias against the glycolytic direction, all right? They're sort of positive in standard state free energy. And we had to work by draining the intermediates to pull them in the glycolytic direction. You can probably guess how gluconeogenesis or the gluconeogenic glycolytic pathway couple is going to work. It's going to use this design, right? Okay, and we'll start looking at that in the next video.